Yes, here we are. It's the physics video lecture, Physics 203, video lecture 16. And we're moving on to a new topic in Hamiltonian mechanics called Poisson brackets. And these Poisson brackets look just like the commutators that you talk about in quantum mechanics. So classical mechanics had them first. So let's have a look at Poisson brackets. Goldstein has a lot of material on this. I'm just going to give us the basics. So we're going to look at a Hamiltonian system. Hamiltonian system of coordinates, momenta, and time. We could write vectors here if we wanted as well, okay? N degrees of freedom. And we're just going to form a new object here. Okay. And F equals F of Q, P, and T. So we have a Hamiltonian system and it's Hamiltonian. And now we have another function of the coordinates, the momenta, and time. And I'll write that explicitly. Function of the coordinates, momenta, and time. Okay. So the Hamiltonian, of course, is a function of the coordinates, momenta, and time. But this function f could be any number of things. It could be angular momentum, linear momentum, that type of thing. Okay. So what we now do is form a certain set of derivatives. We'll take the complete time derivative and we've got df dqi qi dot plus df dpi pi dot, and outside of the sum we have not equals. Outside of the sum we have the explicit time derivative. Okay. But from Hamilton's equations we know we have a way of expressing q dot and p dot. Okay. So let's continue on using Hamilton's equation. Directly underneath here we have the sum over I df dqi, and now remember qi dot is partial h with respect to pi, and we're going to have, I'm going to put the minus sign in right away, we're going to have df dpi, and pi dot is minus partial h with respect to qi. And outside of the, and put these right here, outside we still have df dt. So this collection of derivatives gets a shorthand form, and so we'll leave enough space in here to write any definitions we need. This is called the Poisson bracket of f and h. Okay, this set of derivatives, and we still have the explicit time derivative. So that's called the Poisson bracket, and because Poisson brackets are sometimes introduced with a different convention in terms of what derivative is taken first, we'll go ahead and write qp here for the moment. So we do the q and then the p, and then subtract off the p and then the q. So that's called the Poisson bracket. Maybe a different color for that. That's that whole thing here. Poisson bracket of f h. Okay. And I've got room over here. So we can write this. So dt equal to f comma h plus partial f with respect to time. Okay. So that's certainly a shorthand. And what does it mean? Well, suppose that f is a constant of the motion. Okay. In other words, suppose f is a conserved quantity. We refer to it as an integral of the motion. Integral of the motion. So this is just standard terminology. So we can call it integral of the motion, or sometimes it's called a constant of the motion. Okay. And we know those as conserved quantities, for instance. In that case, then df dt is equal to 0. Right? Conserved quantity, df dt is equal to 0. And then we have an f comma h plus partial f with respect to t is equal to 0. And then the most important cases, when f is not explicitly a function of time. So if we don't have the explicit time dependence, then the Poisson bracket of f and h itself is equal to 0. So I'm going to continue that thought right here. If f is not explicitly a function of time, that's the way we say that, then the Poisson bracket of f and h is equal to 0. So this is a way to characterize conserved quantities, okay, with their Poisson bracket. And like I said, on starting this is the formalism that you're going to find in quantum mechanics as well. Okay. So we'll continue on with this. So we have this definition. Make sure that it's this combination of derivatives. And since it is just a combination of derivatives, there are certain rules that we're going to write down for Poisson brackets in a moment. Okay. That we can get properties of this thing independent of taking all of these derivatives. Good, so let's have a look at that. Immediately we want to do a couple of examples. And the most basic one is if we let f be the Hamiltonian itself, then clearly this equals 0, and of course we're just saying the energy is conserved. That's the first example of Poisson bracket. I want to give a little more or a little less trivial one. And so our next example is the central force. So here we have a couple of steps. We imagine we start with the central force Lagrangian, F m r dot squared phi dot squared minus u of r. Okay, so we've been there before. The Hamiltonian turns out just to be t plus u, but we've done this. I'm just going to write it out. It's p sub r squared over 2m plus p sub phi squared over 2mr squared plus u of r. Okay. So everybody remember this, and if you don't, make sure you know how to go from here to here. Of course, that's a really crucial one. So our central force Hamiltonian, and now what are the conserved quantities for this central force Hamiltonian? We already know that the Hamiltonian is conserved, the energy is conserved in the central force problem. Basically when you don't have explicit function of time, right? You know it's conserved. But what else is conserved? The angular momentum is conserved. So we know that angular momentum P sub phi is conserved. So let's see what that looks like in the Poisson bracket formalism. So this is what we have to evaluate over here. So we want to calculate P sub phi h. I'm just going to write QP like this. And let's go ahead and expand out the whole definition first. So it's sum over d P sub phi d Q sub I d h d P sub I minus d P sub phi d P sub I d h d Q sub I. Okay. So what do we have here? Partial of any momentum with respect to any coordinate is trivially zero. Okay, momentum is itself, so it's not a function of the coordinates. Remember, the Q's and P's are, we have them up here. The Q's and P's in the Hamiltonian formulation are independent coordinates, independent variables. So these are all trivially zero. And then here we're actually going to have dP sub phi with respect to dP sub phi, which will be a 1 among these variables, but the dH d phi will be equal to 0. So I'm going to write, for here we have dP sub phi, dP sub phi, that gives us 1, but dH d phi, right, that's what I'm talking about, the corresponding Q, is equal to 0. So yeah, this is therefore equal to 0 as it had to be. Okay. But this is how you could expand the whole thing out. Maybe I should even expand this out a little more. What we had here was dP sub phi d P sub phi, dH d phi. We had dP sub phi dP sub r, which was, right, that was the other momentum, the r momentum, P sub r, dH dr. And this, of course, is trivially 0, right? P sub phi partial with respect to a different momentum is 0. So this one was 0. This was, yeah, this one was not 0, but this was. So yeah, we got zeros everywhere. So that's how that is done in practice. So there are algebraic rules for this.
I'm going to write down the definition once more.
Okay, so I'm writing down the definition once again. In fact, why don't we remind ourselves, dft sum over df qi h pi minus and outside this thing right here. So this, once again, was Poisson bracket FHQP. Just want to note, different books will define these things differently up to a sign. So what do I have here? So FHQP, we could call this HFPQ, right? You just reverse the order up here, and then you reverse the order down there. So some books will use this form P and Q first, Q and P first. So okay, we're always going to assume start with the different derivatives with respect to Q. Okay, it changes nothing about the overall definition. Also, so now that we have this with regard to the Hamiltonian, the Poisson bracket can also be defined for two functions, f and g. Fg Qp, which is always going to be understood, will just be the sum over df dqi dg dpi minus the opposite df dpi dg dqi. And this is the one we want to talk about on a little more general terms, because of course it contains the previous definition right there in it. So, properties. So I want to list a couple of properties here, and they're basically trivial enough just to write them down and inspect the definition and then check them off. So first of all, as just noted up there with these alternative definitions, Fg is minus GF. Okay. If you take the Poisson bracket with a constant equals 0, so if C is equal to constant, then if you have a sum of functions, f1 plus f2 g, then just by the additivity of derivatives plus f2g. Okay. So these are all clear by inspection. If you have the product of two functions, then just by product rules and differentiation, you have f1, f2g plus f2, f1g. So this one too, you can see pretty much by inspection, because it'll just be the product rule of taking derivatives, you know,
first function here.
And the same for a formula with partials. They'll do it directly under these. These are just applications of differentiation rules. But they turn into a sort of a complete set of algebraic rules for the Poisson brackets. I want to do, okay, one more. If you have the partial f and g, then you'd have partial of Poisson bracket of the partial plus f. Again, no, that's a g. Again, these are just direct applications of rules of differentiation. E.g., pt, like this. Now, finally, though, we come to what are called the fundamental Poisson brackets. So these we want to pay a little more attention to. Suppose we want the Poisson bracket of f with p sub k. Poisson bracket of f with a particular out of p sub 1 to p sub n, the kth momentum. Let's go ahead and apply the definition. We have df dq sub I df dq sub I dp sub k dp sub I minus, we'll need some there, minus df p sub I dp sub k dq sub I. Okay, so trivially, these partials are all going to vanish. These are all limited sum. Okay. So here we have a delta ki. So we have sum over df q sub I summing over I. Then we have delta ki, because only one of these is equal to 1. The rest are equal to 0. And of course that picks off the kth one here, so that is equal to df dq sub k. And we can do the same thing. F q sub k sum over partial of f partial q sub I q sub k p sub I. Of course, these are all going to vanish trivially. Then we have minus f p sub I q sub k dq sub I. So again, these vanish, and we're just left with this one. These are inside the sum. What do we get over here? Minus df dp sub k. So let's list those now. We have f p sub k equals f q sub k f minus df dp sub k. Now what we can do is let f be equal to p sub I. Now let F equal P sub I in here. You're gonna write these down. P sub I, Q sub K. So here's what I want you guys to do. Go ahead and make sure you see these. So these are the fundamental Poisson brackets. Go ahead and, I'm just gonna write here, homework. That'll just give you just enough of a review of what I'm talking about here. Nothing here is difficult at all. Okay. It's essentially already all up on the board, but this way, if you go ahead and write these out and calculate them, make sure you see them, that'll be a good thing. Is that all complete? Yeah. So you can see what we're doing. If we plug in P sub I, P sub Q sub I, and these different things here, in these basic Poisson brackets, we get these fundamental relations. Okay. And they look like commutators. Good. Okay, so that is nice to know. So in a sense, there are these algebraic properties of these things. And you can either, when you're doing a problem, you can either go back to the definition and crank it out, or you can use some of these properties, whatever's easiest. Yeah. So yeah, for the homework, just to make sure you go back and nail these down, and then you'll be in good shape. Okay, now I have another related and very interesting application here. Let's see. And these we're just going to do with 1 degree of freedom for Hamiltonians that are with conserved energy. So we will call this a formal solution to Hamilton's equations. And what we're looking at is let H be equal to H of Q and P, no explicit time dependence, and this is going to be one variable, okay, 1 degree of freedom. System with 1 degree freedom. Okay. So we know that FH is equal to dF dt, okay, because there's no explicit time dependence, and F is F equals F Q and P. Okay. So we have that, and we know the definition of this Poisson bracket. So what we're going to do is let F be equal to the coordinate itself, Q. Then we have Q dot is equal to FH. And interestingly, the second derivative is equal to the Poisson bracket of this with the Hamiltonian, and so on for higher derivatives. So we could have, for a third derivative, this Poisson bracket, or this object here in the Poisson bracket with h again. So I'll even write one more, and instead of putting the dots here, let's go ahead and write out the explicit time derivatives for the moment. Okay, dq dt d squared q dt squared. Okay, and would be equal to fh h how about that? Okay. Well, formally, that's why I'm calling this formal. You could just do this indefinitely. Now, we could use this to construct a Taylor series solution. Let us use this to construct a Taylor series solution. So I have two really good problems that we're going to use this for. And I'll start both of them and make them a homework, and I think you'll enjoy it. So first of all, let's just write down what the Taylor series is. So we have, since f is q, we have q of t is equal to q of t equals 0 plus dq dt evaluated at t equals 0 times t plus 1/2 d squared q dt squared, always evaluated at t equals 0 t squared, plus and so on, all the higher derivatives. And now it looks like if it's an infinite series, you don't want to do an infinity of these, but we'll see in a moment that we don't have to necessarily. Okay. So yeah, this is a Taylor series. This is the derivatives evaluated at 0, t squared, t cubed would be the next one, and so forth. So there's your formal solution right there. You have to calculate all these Poisson brackets, the first one, the second one, the third one, and I'll show you two examples. Actually, I'm going to start each example, and we'll do both of them for homework, or you'll complete them both for homework. So the first example is free fall. We know everything about free fall, right? So what is the free fall Hamiltonian? H is p squared over 2m plus mg q. Okay, so q is my vertical direction. That's the potential energy, mgh, mgq. So there's my Hamiltonian, and I have to form some of these derivatives here. Right. The first, the second, the third. So, right, because we want this Taylor expansion. Q0 is just going to be an initial condition. dq dt is going to be linear in time. d squared q dt squared evaluated at 0 quadratic time and so forth. So what do we have for QH? What we have to do is evaluate these and then hold on to the result, but also take its result when time equals 0. So QH is equal to Poisson bracket Q with P squared over 2M plus MGQ. And now we can use our rules. We have Q P squared over 2M plus Q MGQ. If we want to, we can write 1 over 2M, so we need Q P squared plus mg, I'm pulling out the constants, q. Okay. So you guys want to figure out what this is. Okay. Well, this is clearly 0. What about q p squared? You got a couple ways to figure this one out. And so that'll be for homework. This one's already 0. So you're just going to have q and p squared. Actually, for the purposes of the next one, I have to write this down. So you're going to get this one. And it's going to be the whole thing, by the way, is going to be P over M. It's going to be P over M, and so you're going to have, just to show you how this goes, so Q of T is going to be Q naught plus P naught over M T plus so on, okay? So that's the linear part, and you recognize this. This would be MV over M, so this would be Q naught plus V naught T, okay? So the second one, I'm going to write question mark here, because we're not done yet. So the second one I will leave for you guys to do. So next we need Q, H, H. Now we already found this one. This was P over M. Okay, so we're going to have P over M and then the H is P squared over 2M plus MGQ. So you see how that goes down. Like I said, you can do the definition, or you can look to some of your fundamental relations here. Now what's going to happen is you're going to generate, see, this is the law of free fall, we know this, you're going to generate negative 1/2 GT squared, right? So we know what we're headed for. what that means is this second one is going to equal some constant. Because this is the g over 2t squared. This is the 1/2 second derivative of t squared. Okay. So you're going to get negative g out of this thing. And you can see it really well here, actually. This one with p squared is going to go away, it'll vanish. P over m, you're going to have the m, you can pull out the g, p, q, going to be, it's still up there, it's not. Okay. You're going to get the -1 out of that p, q. Okay. You get the -1. Therefore, because this is going to turn into a constant, that's the end. There are no infinity -2 derivatives left, right? This ends at the second derivative, and so it wasn't so bad after all. So yeah, make sure you understand this one well, and this next one's going to be a little more challenging, but also really interesting. Okay, so homework is just to go through this and make sure you obtain this. It's actually, we're actually looking at it already, in essence. So our second example is going to be the harmonic oscillator. We'll use P and Q again. Also homework. Harmonic oscillator. Harmonic oscillator. So here we have H is equal to P squared over 2M plus K Q squared divided by 2. And we have to, this time we actually have to do an infinity of these, but we only have, turns out we only have to do 4 or 5. So for the harmonic oscillator, and you know we want Q of t is equal to Q0 plus dq dt 0 Q plus 1/2 and so forth, right? The same thing. But if we remember, if we're doing it, not Q's, these are T's. These are T's plus T squared, right? Now on this one, we can recall what we're actually going to get. Recall Q of t is equal to A cos omega t plus B sine omega t. And these are two infinite series. And in fact, in this form, because when t is equal to 0, you just have A, this is Q naught cos omega t. And when you take a time derivative, you get omega times B cos omega t. Okay. So here, let's write this. Q dot equals minus omega A sine omega t plus omega B cos omega t. I'm just looking at the initial conditions. So when we take time equals 0 here, this vanishes, we get omega B. Okay. So B is equal to naught divided by omega, and we would say that is P naught divided by M omega. So what we're looking for is P naught over M omega sine omega t. So this is what we're going to have to find. Okay. Furthermore, cos omega t goes like this. So you have to remember these power series. You have 1 minus 1/2 omega t squared plus 1 over 3 factorial omega t to the 4th. Oh, factorial. No. 4 factorial minus 1 over 6 factorial omega t to the 6th. And the sign goes as omega t minus 1 over 3 factorial omega t cubed plus 1 over 5 factorial omega t to the 5th. Okay. So what you're going to have when you generate all of these Q, H, H, etc. When you generate all these Poisson brackets, you're going to generate all of the powers, and when you look at them closely, you're going to have the even powers belonging to the cosine and the odd powers belonging to the sine, with the P naught over M omega out front. Furthermore, you'll find that when you do, where are we here? When you go through this 4 times, okay, so you do 4 of these, that you run back into your initial one. So the problem is cyclic. So you have to do 4 at most 5 of these Poisson brackets before you arrive at where you started again. It goes through cyclically, and that way you can just by induction declare all infinity of them. So this is a nice problem. You know, like I said, you have to do about 4, 5 of these tops, and they're not complicated. It's always just P's and Q's here with each other. And you will end up generating this answer here. Yeah, so your infinity of these will break down into cosine omega t of this form, sine omega t of this form here. You know, write these out clearly. I can barely read them myself, okay, but you got to know this cosine and sine power series. Oh, one more thing. What is the omega? We will find, we know that omega squared is k over m. Okay. So your omega will be root k over m. And that'll all come out. It's a really great problem. It's a really great problem. Okay, let's see how we're doing time-wise. Whoa. Okay, anything else? So this stuff I just did to make sure I generate the right expressions here. This is the formal solution of the harmonic oscillator. And maybe I'll just write down the first of those Hamiltonians, just to make sure we see. Because you'll find them alternating, and before you know it, good. So we're looking at Q, H, that would be our first one. Q, E squared over 2m plus KQ squared over 2. Okay. Let's pull the constants out while we're at it. So then we would have 1 over 2m q e squared, which we've done already, plus k over 2 q squared. Okay. So this one you're gonna get rid of, this one you're gonna get 2p over 2m, so you get p over m like we did last time. And then you go back into this one here. So you go back in with the p over m with the Hamiltonian, and then the p's vanish against these, and it's going to be the PQ that gives you your next contribution, okay? And so that's going to alternate, and by the time you've done 4 of them, you've come full circle, so to speak. Okay, so yeah, enjoy that one. This first one, truncated because we ended up with a constant. What happens with this, it just keeps alternating between P and Q, and you then end up generating this expression here with these cosine and sine infinite power series. Okay, so that, actually there's a lot more about Poisson brackets, but those are the ones I'm going to assign homework problems on. Okay, I think what I'll do is leave it at that for now. We have a lot of other topics. This may be our Poisson's bracket section. So yeah, enjoy these, and we'll see you next time.